Hi class, in chapter 5 we're going to start off with section 1 called polynomial functions. And even though you've talked about polynomials in previous classes, the topics covered in this chapter are going to be new for college algebra. And a lot of these will be concepts that you've never seen before. And I really encourage you to get down and study and make sure that you understand all the definitions and all the theorems and all the different nitty-gritty parts of this section, because we're going to start off with polynomial functions, but then we're going to apply those to rational functions later on in the chapter and to other functions as we move on through the book. And so this is really setting the groundwork for the rest of college algebra. The first thing that we normally do is define our functions and define the terms that we're using. So we have here a definition of a polynomial function. Now I want to point out some of the language that we have here. When it says a sub n, x to the n, the little n here is called an index. And so the index here matches the exponent over here. And it's a little bit wonky to read, and if you're not familiar with this way of indexing our numbers, it can get slightly confusing. So I put a polynomial here for us to look at, and I want to talk about the different parts of it. And so we have a sub 7 is 5, meaning the coefficient of our x to the 7th power is 5. And then we have a sub 6, the coefficient of x to the 6th is 1. And then we have a sub 5, meaning the coefficient of x to the 5th. Well, I don't see an x to the 5th in that function above. Well, that means that its coefficient must be 0. And we have a sub 2. The coefficient of x squared is negative, so we're going to put the coefficient is negative 1. And then a sub 1 is going to be negative 9, and a sub 0, meaning the coefficient, that's not a coefficient, it's a constant, because there's no variable with it, is negative 4. So hopefully, have I written it down here, it's going to be a little bit clearer how we're indexing these, and that the a's are the coefficient pertaining to the power that matches the index. And so the new word here is index. We have the degree of this polynomial is going to be the highest power. So that's going to be the 7th power is also the 7th degree. And then we also have the leading coefficient. The leading coefficient for this is 5. And then the other thing it says about our polynomial is that it says the domain of a polynomial is the set of all real numbers. And that's for any polynomial that you have. So the domain, if I ask you what's the domain of a polynomial, and that's a question that's pretty much on every test from here on out, the domain is going to be all real numbers, in other words, from negative infinity to positive infinity. Now the range was going to be different depending on the equation, but the domain will always be all real numbers. One more topic that I really want to make clear. You want to make sure that n is an integer and that it is greater than or equal to 0. And this is going to be important. We're not going to have any fraction exponents. We can have fraction coefficients, but we can't have fraction exponents. We can have any number as a coefficient, but we can only have whole number positives and zeros for our exponents. We're going to look at a few functions and see if they satisfy the definition of polynomial functions that we have here on this page, and also see if we can come up with the answers to the degree and the leading coefficient. Question number 1 says to determine which function is a polynomial function. So let's first do that first part before we look at the second step. And when we look at number 1, we see f of x is equal to 1 minus 1 over 2x. Now, it's not explicitly stated in our definition of polynomial function, but you cannot have any variable in the denominator and then still call it a polynomial. If you're not sure of what I'm saying, let's take this function and rewrite it one time. So I'm going to rewrite this, moving the x to the numerator, or outside the fraction even. I'm going to say 1 minus 1/2 times x to the power of -1. You see, because x was in the denominator, when we move it up or when we move it out of the fraction, it gets a negative exponent. And that negative exponent, it does not satisfy the fact that our exponent needs to be an integer that's greater than 0. And so this is not a polynomial. Therefore, we don't have to answer the rest of the questions about it. Let's look at number 2. And it's written as x times x minus 1. Let's just multiply that out. We get x squared minus x. And looking at this, does this fit the definition of a polynomial? Do I have variables with powers that are whole numbers, integers, positive integers? And that's an invisible power of 1 and a power of 2. So that's okay. So yes, this is a polynomial. And because it's a polynomial, we're going to look at the rest of the question. It says, write in standard form, which actually we already did. This is standard form. And standard form also means that we're going to put it in decreasing order of powers. So we're going to put the x squared first, and then the x to the 1 next. We want to state the degree. The highest power here is 2. We're going to say it's degree 2. And the leading coefficient is the coefficient in front of our first term, the one over here that's missing, and so its leading coefficient is 1. And the number of terms it has is 2. Okay, we're going to move on to a few more definitions. Now the definition of a power function is that it's a polynomial function of any degree, but is the only term that's in that polynomial is its first term. So it's a monomial, meaning it only has one term, and that's our leading term. And so we're going to take a look at some of these power functions. We're going to group them by their powers, and we're going to look at the ones that have even exponents, even powers. Now question 3 asks us to use a graphing utility to graph the following power functions and explore the properties mentioned above. And they ask us to graph x squared, x to the 4th, and x to the 6th. So we're going to look at the graphs of x squared. What will x to the 4th look like? Will it be greater than or will it be less than x squared? Well, it actually depends on which interval we're talking about. So let's go ahead and take a look at it. And when you see this, you can see that they have some points in common, and then some places where the graph is greater than, and some places where the graph is less than. Let's continue on the pattern. Let's look at f of x is x to the 6th, and you can see that this also goes through the same points. So let's look at what points they go through. All three of these functions have these 3 points in common, and we would assume that any other function that has an even power would also have those points in common. And so that's one of the things that we see on our properties of power functions, that when the n is even, it goes to the 3 points, -1, 1, 0, 0, and 1, 1. And notice that because they have even powers, these are actually even functions, meaning that they are symmetric with respect to the y-axis. So if you can see that symmetry with the y-axis being shown, the domain for all functions, for all polynomial functions, is always going to be the set of real numbers. But the range is going to be slightly different. Notice that the lowest number here is 0, so the range is going to go from 0 to infinity, meaning it's the non-negative real numbers, including the 0. I want to point out one portion of this. Now, when we look at the functions, we have x to the 6 is greater than x squared on certain intervals. That would be from 1 to infinity, and also again over here from negative infinity to negative 1. And we can see that in between, we actually have quite the opposite. We have x squared is greater than x to the 6th on the interval 0 to 1 and on the interval negative 1 to 0. But we have that they're all equal to each other at negative 1, at 0, and at 1. So you can't include those in our greater than or less than symbols. And you see that behavior talked about on the properties of power functions. Last but not least, we talk about the end behavior. And notice that for all of these graphs, as my x increases and as my x decreases, both sides of the graph are going up. And yeah, they both are going towards positive infinity. You see, as my x increases, then my y increases. As my x decreases, my y increases. And that notation says as x goes to positive infinity, then y, or f of x, goes to positive infinity, and x goes to negative infinity, and also my y still goes to positive infinity. And these are what we call limits. Now I just want to look at the graphs of x cubed, x to the 5th, and x to the 7th. And we're going to look at this in conjunction with a chart about odd functions, because these are all odd powers. So the first one we're going to look at is x to the 3rd, and it should follow the behavior that we're used to seeing. But we're going to see how that behavior continues as we look at similar functions. So when I look at x to the 5th, you should be able to see that sometimes x to the 3rd is greater, but sometimes x to the 5th is greater. We also see some intersection points happen at 0, 0, negative 1, and 1, 1. And so we want to see if that intersection pattern continues as we look at x to the 7th. And yes, we have 1, 1, 0, 0, and negative 1 also showing up. And we can talk about the different parts of this. These odd functions, like all odd functions, are symmetric about the origin. And so that the point 1, 1 gets reflected through the origin to negative 1. And you see that it's increasing on the entire function. The domain is all real numbers because it's a polynomial, and the range for this one happens to also be all real numbers. Now once again, we might see that x to the 7th is greater than x to the 3rd, and that happens on certain intervals. It happens on the interval 1 to infinity. The difference is it happens from negative 1 to 0 over here. So those are the two intervals it happens on. And then alternatively, we have x cubed greater than x to the 7th, and that is on the interval from 0 to 1 and negative infinity to negative 1. We'll also see that as my x increases for the end behavior, as my x goes to infinity, my y value, or my f of x value, also goes to positive infinity. You can see that going up. But as my x goes to negative infinity, as I move left on this graph, then you can see that the y value goes to negative infinity, and it goes down. And those are the properties of odd functions. Now that we've looked at power functions that are odd and even, we're now going to look at polynomial functions that are not power functions, and look at the x-intercepts to tell us a lot about the function. We can look at the graph of a function and know a lot about the x-intercepts based on the behavior of the graph as it either touches the x-axis or crosses the x-axis. And we can learn a lot about the function by looking at the end behavior as it goes to infinity and negative infinity. Let's look at the definition of real zeros. It says that f is a function and r is a real number for which f of r is equal to 0. That is, the y value is 0. Then we call r a real zero of f. Now, looking at this graph, we can just put some values that make sense. This is my r because f of r is equal to 0. Because the y value here is 0, let's say this is 3. If we know that r is a real zero, then we have several other statements that are equivalent. So we would say 3 is a real zero of f. And we'd also say 3 is an x-intercept of the graph of f. And then we'd also say x minus 3 is a factor of f. And we'd say 3 is a solution and a real solution to f of x is equal to 0. Now 3 was just an example. I just pulled a number that made sense, but we could actually say the same thing about all of these x-intercepts over here. Since we see that those are x-intercepts, so therefore satisfying the second statement, then we would also say that those are real zeros because that's an equivalent statement. We could also say if this was r is equal to 5, then x minus 5 is also a factor of this function. And so let's go ahead and see what this looks like as we look at properties of a function. So for question number 5, it says form a polynomial whose real zeros and degree are given. And I left on this page the definition of real zero and also what its equivalent statements are to help us form this polynomial. And I just want to go through each part. We're given 3 zeros, so we were given the fact that these were zeros. That was already given to us. Next, we know that each of these zeros is an x-intercept of the graph. Let's see if that helps us. I'm going to sketch a graph real quick. And on this graph, I'm just going to put the values that we were given. So -4, 0, and 2. And so our x-intercepts are -4, 0, and 2 because it says each of these r's is an x-intercept of the graph. Well, that's interesting to know, but that doesn't really help me come up with a polynomial. Let's try the next one. It says x minus r is a factor of f. What this is saying is, I can say my function is a bunch of things that are going to be multiplied in the form of x minus r. And my first r is -4. My second r is 0. My third r is 2. So, simplifying this, I get x plus 4 times x minus 2. And if I want to rearrange it a little bit, I'm going to get x times x plus 4, x minus 2, which is x squared plus 2x minus 8. And then we get x cubed plus 2x squared minus 8x. And so by starting off with all of those factors being individual little factors written in this format, I was able to simplify and multiply and get my function. And here is my polynomial. It is third degree because my highest power is x to the power of 3. And there we go. And so I want to sort of check the work that I did. I came up with a polynomial, and what I want to do now is graph that polynomial that I came up with using one of our graphing utilities. I'm going to use Desmos.com, and I'm going to see if it has the x-intercepts that I said it was going to have. So I'm going to look for -4, 0, and 2 on that graph. Let's pull that up right now. And so typing in our equation, that's what I get. And notice I have the -4, I get the 0, and I have the 2 as my x-intercepts. So more than likely I came up with the right function. This is a nice visual way to check. We have another definition called the real zero of multiplicity m. It's actually very easy to identify the multiplicity of each real zero. This definition makes it look more complicated than it actually is. Why don't we go through a few examples so that it helps you understand what this definition is saying. In our first example, we see that we have several factors. This is actually a 5th degree polynomial, but it only has 2 different real zeros, and each of these real zeros has a different multiplicity. Let's look at each factor individually. If my factor says x minus 1, then that means that 1 is my real zero, and then it has a multiplicity of 2. If my other factor is x plus 4, that's actually x minus -4, so my real zero is -4 with a multiplicity of 3. And so we have to remember that when we look at each factor, when we're pulling out the real zero, we're going to pull out the opposite sign. When it said x minus 1, we're going to pull out a positive 1. And when it says x plus 4, we're going to pull out a -4. But then each of these real zeros has a multiplicity that matches the power on the function. Very easy, right? So taking a look at the definition, why does it say m as a power and then m plus 1 as another power? Well, basically, here's an example to go with that. For g of x, we see it says x minus 5 squared times x minus 5 times x plus 7. It would be incorrect to say that the 5 over here has a multiplicity of 2, even though that's the power on it. Why? Because it's not written in simplest form. If we were to properly write this, we would get x minus 5 to the 3rd power, and then x plus 7. And so then our 5 has a multiplicity of 3, and our -7 has a multiplicity of 1. So we just have to be careful that we have it written in the most concise form before we pull out the multiplicities. That's all that this definition is saying. But the multiplicities are very easy to identify when you just look at the power once it's written the correct way. Question number 6 asks us to form a polynomial whose real zeros and degree are given. And a lot of it is similar to the work that we did in number 5. But we do have different multiplicities given, so we want to take that into account. Our first factor is going to be x minus a -2. And that's going to be a multiplicity of 2. Our next factor is going to be x minus 4. And that's going to be multiplicity 1. You don't have to write the ones down because we know what that is. And then we're just going to simplify. And once we simplify, we do want to write it as a function. And that should be our polynomial. If we graph this, we should see that it goes through our zeros in a certain way. So once again, just sort of verifying our work, let's put that function in and let's see what our intercepts are. I have an intercept at -2 and I have an intercept at 4. And you can see, even though it touches the x-axis at these values, it doesn't behave the same way, and that's because of the multiplicities. So we have the behavior of the graph in relationship to real zeros of even and odd multiplicity. I just want to point out that when you see here that this crosses the x-axis, that is an odd multiplicity. That's like it was only a root, or it was only a real zero, or it's only an x-intercept 1 time, or maybe 3 times. And so this would have a power of 1 on it. But when it touches the x-axis and it stays on the same side, it doesn't cross it, that's when you have real zeros of even multiplicity. And if you think back to graphs that you might know, like x squared, it touches the 0 and it comes back up. Those are even multiplicity. But when we think about the power functions that had odd powers, it crossed the x-axis. And so we've seen this behavior before. We have odd multiplicity here, even multiplicity here, odd, and odd. And so when you look at a graph, you can know certain things about the multiplicity of the roots just by the behavior of the graph at each of those real zeros. Taking what we just learned and applying it to the graph that we just did, we can see that the -2 was a real zero of even multiplicity, and that the 4 was a real zero of odd multiplicity, because at -2 it touches the graph and comes back, and at 4 it crosses through the graph. And that matches the information that we were given, the information that we started off with. So it looks like we did a great job and that we're learning things about the multiplicity of graphs. I want to point out real quick, though, that the question says form a polynomial and it doesn't say form the polynomial. Why does it say that? Well, we could have made a bunch of different polynomials, and we could have done something instead of saying what we did. Maybe we could have multiplied everything by a factor of 3. And this was a possibility. This would also have all the same zeros. It just would be a graph that has that would be stretched vertically. Also, we could have done the final answer as 3x cubed minus 36x minus 48. Right? And if we have graphed that, we would see that it has all the same values other than the stretch. So all the x-intercepts would be exactly the same. But we were only asked to come up with one, and for the most part, most of us, if given a chance to come up with our leading coefficient, we would just come up with 1 because that's easiest. To build on what I was just saying, notice that this question does ask us to find the polynomial. That means that we actually have to take the a into account, our leading coefficient into account, and to make sure that when we're done, this is correct. So when I first set up my polynomial, it's going to be f of x is equal to a times x minus -2, x minus 0, and x minus +2. And simplifying that, I get a times x plus 2, x, and x minus 2. I'm going to multiply that out. I could easily make the a into a 1 and say here is a polynomial, or I could turn it into a 2, and all of those would be correct if it said find a polynomial. But this one says to find the polynomial, so I'm going to plug in the values. So -4 is my x, and 16 is my f of x. So that gives me so my a is actually -1/3. Let's rewrite my polynomial. My f of x is going to be -1/3 times x to the 3rd minus 4x. I'm pulling that from right here, but plugging in my value for a. Alright, now that I have that polynomial, let's go check on our graph. We're checking to see that it has the zeros -2, 0, and 2. And we're also going to check that it goes through the point -4, 16. I have the graph here, and I went ahead and labeled the point. You can see that it does go through the point -4, 16. It also has the zeros -2, 0, and +2. So it really, we know we came up with the right function because it has the correct intercepts, and it also contains the extra point that they gave us. This next theorem is about turning points, and first of all, we should define turning points, and they're basically the maximums and the minimums of the functions. And each of those peaks and valleys is considered a turning point. It says if a polynomial is of degree n, then the graph has at most n minus 1 turning points. That means if I have a polynomial of degree 4, it has at most 3 turning points. So I have a local min, a local max, and a local min. I have up to 3, but not more than 3. But I don't have to have 3. Think about the graph of x to the 4th. It only has 1 turning point, and that's okay. But you're only going to have 3 at the most, but you could have less than 3. Alternatively, if I was given a graph and I could count the number of turning points, then I know the degree has to be at least 1 more. So if I'm looking at this graph and I'm saying, oh, I see 3 turning points, at the least it has to be degree 4. But I might be able to say maybe that's degree 6 or maybe degree 8. It just has less, the relationship of the turning points to the degree has to be less than. The turning points has to be less than the degree. For this one, it looks like, well, it could be potentially degree 2. That's the least degree it could have when looking at some graph with only 1 turning point. But it could possibly be degree 4 or degree 6 or degree 8. It just has to be at, the lowest it can be is degree 2. That's what these two theorems say. The next theorem that we have is about the end behavior of the graph of the polynomial function. And there's a lot of technical text in here, but basically it's saying that the graph, the end shape, it might have some turns in the middle, but the end shape matches its power function. Let me give you a few examples. If I'm looking at the power function x to the 6th, its end behavior goes up to positive infinity on both in both directions. So if I'm looking at any polynomial function that's degree 6, is going to have that same end behavior. It's going to have a maximum of 5 turns, but it could have less than 5 turns, but it's always going to be pointing up in both directions. This is a potential x to the 6th polynomial. And notice it has 5 turning points, but it could also have less than that. This one is also an x to the 6th polynomial. It has 3 turning points, which is less than 6, and its end behavior matches the x to the 6th. Alternatively, let's look at the end behavior of x to the 5th. It has 1 going up and 1 going down. So all x to the 5th polynomials, no matter how many turns they have in them, will have this end behavior. This is a graph of a potential x to the 5th polynomial. It has 1, 2, 3, 4 turning points, but its end behavior, one goes up and one goes down. So it matches the same behavior of the power function. And so we're able to tell if there's a function that's even or odd by looking at the end behavior of the graph, if they both go in the same direction or if they go in opposite directions. For number 8, it gives us a polynomial function that's already been factored for us. I want to point out that one of the factors is just 4, and that happens to be the leading coefficient. It's not written in the format x minus r. The ones that are written in the format x minus r is x plus 4, which is another way of saying x minus negative 4. What's our real 0 from that factor? Our real 0 is negative 4. It has a multiplicity of 2. And because it's an even multiplicity, it touches the x-axis but does not cross it. Let's look at our other factor. It says x plus 3, which we know is x minus negative 3. So our real 0 is negative 3 with a multiplicity of 3. Because that's odd, then we know that it crosses the x-axis. If I were to multiply all of the factors out, I would see that I have a degree 5 polynomial, which means you have 4 as your maximum number of turning points. Now we don't know how many turning points this has, but we know it has a maximum of 4. And the end behavior of a polynomial is going to match the power function. So it's going to have one side going up and one side going down. I actually know a lot, and I can sketch a little bit of the graph. I know it has an x-intercept at -3. I also know it has an x-intercept at -4. I know that the behavior over here goes down, and the behavior up here goes up. I know it touches, it comes back, and then I know it crosses. So it does something like this. Now there might be other turns, other places. Right now I only see 2 turning points, but that's what we see. And we know we have those x-intercepts, and we know the end behavior of the graph. One goes up and one goes down because it matches the power function over here. And so that's how we use all of the properties and all the theorems to be able to come up with a great idea of what the graph looks like when we're just given the polynomial function. Number 9 says to identify which of the graphs could be the graph of a polynomial function. So this leads us to the last property I'm going to talk about today, which is the fact that the graph of a polynomial function must be smooth and continuous. By smooth, I mean it has no corners. So this graph is not possible. It's not possible to have written that with a polynomial function because you can see it has that really sharp corner right there at the origin. This first graph, it is smooth because when you go along it, there's no sharp turns. But it's also going to be continuous. Now all of our graphs so far have been continuous, but that basically means you can graph it without lifting up your pencil. We'll see later on in this chapter that there are some graphs that you would have to lift up the pencil because they have asymptotes, and they have things that where the graph is not continuous. But for number 9, the first graph can be a polynomial function. The real zeros are at -1. It has a 0 at -1, and it has a 0 at 2. And the least degree this polynomial could have, well, let's see. It has 1, 2, 3 turning points. So since it has 3 turning points, it must be at least 4th degree polynomial. So make sure that your degree is always at least one number more than the turning points. Okay, let's try to apply what we learned and see if we can come up with a polynomial function that has this given graph. So when we look at the x-intercepts, we see -1, 1, and 2 as our x-intercepts. At all of these x-intercepts, the graph crosses through, so they're all odd. And since we're coming up with a function, let's just make it easiest on us. Let's say that they are multiplicity 1. And so our factor is going to be x plus 1, x minus 1, and x minus 2. So we're going to come up with a polynomial. Now we don't know what its leading coefficient is, so I'm going to put a. Then I'm going to multiply everything out. Okay, and then now that I've multiplied it out, I'm going to take this point that I know, this extra point, which is 0 and -1. In other words, I know that my x is 0 and my f of 0 is -1. So I'm going to replace that in here. -1. Now that I know my a, I can take it and plug it back into this function, and I'm going to get my function is -1/2 times x cubed minus 2x squared minus x plus 2. And there you go. You always want to start off by building up all of your factors. First of all, by looking at the x-intercepts and making sure you change the signs, plugging it into our generic formula for a polynomial function, and then multiplying it out so that you could solve for your specific a. And then you have your function. And that's all of section 5.1. It's a lot of stuff. You need to practice it. You need to get familiar with all of it. You need to do the quiz. You need to do the homework. There's a lot of stuff in here that really needs practicing so that you become a master at all of these topics.